Hello, everyone. Welcome back to our deep learning series for physicists. Today, we finally want to shed light on the training process. How can we ensure that the parameters of our network are set in such a way that we obtain the desired physics model? We have already learned about objective functions, for example, the mean squared error. We need to send its information to the network parameters so that they can be optimally adjusted. We will refer to this messaging as backpropagation. The upper left figure shows us a network with input x and prediction z, where for simplicity we will focus on a single node and its parameters weight w and bias b. Of course, we will also consider the activation function sigma. Now we inspect the single network node, breaking it into bite-size operations. Read the upper part from left to right. Input x is multiplied with the weight w to form z1. Then we add the bias b to get z2. We feed z2 through the activation function sigma to obtain the prediction z3. In the lower part of the figure, we see the label y, the actual expected value. We compare the network prediction z3 with the true value y inside the objective function, called L. This set of arrows is called the forward pass. These four lines spell out exactly what you see in the picture. First, w times x gives z1. Add b, we get z2. Pass z2 through sigma, we obtain z3. Finally, the objective function L is the squared difference between the prediction z3 and the label y. How do we transmit the result of the objective function L to the weights w? We calculate the derivative. The chain rule elegantly solves this problem by telling us how the objective function changes when we change the weight w. Read it left to right. The objective function L depends on z3, z3 depends on z2, z2 on z1, and z1 on w. By multiplying those four little slopes, we obtain the needed partial derivative. That backward walk through the graph is called backpropagation. Good news, the same logic gives the slope with respect to the bias b as well. On the screen, you can now see the individual network node with the partial derivative dl dw that is transferred to the weight w. When following the objective function L, the red dot marks the current value of the weight wt. The red line is the derivative. The red arrow indicates the direction for improving the weight at wt plus 1 in order to reduce the yield of the objective function. Assuming a simple physics model of a straight line to describe the data points, the update of the weight to wt plus 1 gives the desired effect of better describing the data, resulting from the partial derivative dl dw. This picture illustrates the heart of today's topic, gradient descent. In plain words, gradient descent asks, which way is downhill on the landscape of the objective function? In order to calculate a gradient, we better average over event samples. Thus, choose a reasonable batch size with k events. Then we simply average the k individual gradients to get one estimate of the slope for w. The same formula applies to the bias b. As we use only a subset of the full training data, the procedure is referred to as stochastic gradient descent, or SGD. All right, time to talk about the learning rate. How big should the step be when updating the weights? The parameter w at step t plus 1 equals the old wt minus alpha times the averaged gradient. Alpha is the learning rate. This update rule is our workhorse. The magnitude of the learning rate alpha is decisive. Is alpha too large and we bounce over the valley? Is it too small and training crawls? The sweet spot sits in between. Cool, but why keep alpha fixed? Let us explore adaptive strategies. Adagrad stores the sum of squared past gradients called nu-t. The learning rate is dynamically adjusted based on the following rule. If the slope has been steep for a while, nu-t grows and the effective learning rate, alpha t, shrinks, giving us finer steps in tricky directions. RMSProp adds a decay term beta. Old gradients fade away, so the learning rate never collapses too quickly. The update formula for the learning rate alpha remains the same as for Adagrad. Momentum adds a completely new twist. Let us combine the weight and bias into a vector theta and calculate the partial derivatives. The nabla operator gives us an optimal direction in the WB parameter space to reach the minimum. We multiply nabla theta with the learning rate alpha and obtain a kind of velocity vector vt. We update the weight w and bias b from time step t to t plus 1 using this velocity vt. Now admire the stabilization. Start from the history of the previous parameters theta t minus 1, far left in the sketch. Then, starting further from theta t, the blue actual velocity vector vt prime would change the direction drastically. However, by weighted vector addition, the velocity vector vt prime is corrected to the red vector vt in order to avoid drastic directional changes. It ends at the new parameters theta t plus 1. Here is the velocity calculation, weighting the previous and actual velocities with beta values somewhere between 0.5 and 0.9. This gives then the new weight w and bias b inside vector theta t plus 1. Computer scientists refer to this procedure as momentum method instead of velocity. The method damps oscillations and steers us along a smoother, faster trajectory. Finally, let us introduce the superstar, ADAM, adaptive moments. It combines the ideas of RMS prob and momentum. Here, AMT is the running mean of gradients which is used to scale the direction of the next step in parameter space. The parameter gamma t is set to 0.9. Nu t is the running mean of squared gradients and is used to adapt the learning rate. The parameter beta is set to 0.999. ADAM cleverly combines the benefits of momentum and adaptive learning rates. In practice, it is often the first optimizer you should try. And that wraps up our cheerful tour from plane gradient descent all the way to ADAM. Thanks for watching, keep experimenting, and as always, happy learning.